This diagram compares the starting mass of the Apollo 11 spacecraft against the specific module that reached the lunar surface. The command and lunar modules departed Earth orbit at over 109,000 pounds. By touchdown at Tranquility Base, the landing vehicle weighed just 10,873 pounds. This 90% reduction in mass is the physical requirement for the journey. Chemical propulsion limits mean every pound of payload requires a disproportionate amount of fuel to move. To make the round trip possible, the mission had to sever and leave behind any weight that was not actively providing thrust. The solution to these propulsion constraints was Lunar Orbit Rendezvous, or LOR. LOR is a mission architecture where the main spacecraft stays in orbit, while a smaller, specialized lander descends to the surface. Executing LOR required a modular spacecraft design capable of multiple engine burns and precise docking maneuvers in a vacuum. Dead weight was discarded the moment its momentum was no longer useful to the current flight phase. The Apollo 11 landing was a process of continuous mass shedding, reconfiguring hardware in space, and managing the limits of the onboard software. Tracing the specific sequence of orbital mechanics and systems crises reveals the technical reality behind the landing. After the ascent through the atmosphere, the spacecraft entered an Earth parking orbit at 100.4 by 98.9 nautical miles. To reach the Moon, the S-4B third stage reignited for the Trans-Lunar Injection, or TLI. TLI is the propulsion burn used to accelerate the spacecraft out of Earth's gravity and onto a trajectory toward the Moon. This diagram illustrates transposition, docking, and extraction. The command module rotated 180 degrees to dock with the lunar module and extract it. The spent S-4B stage was then pushed into a lunar slingshot trajectory, entering a safe solar orbit to prevent a collision. The reconfigured mated spacecraft began a 3-day coast across the cislunar vacuum, discarding the rocket's third stage as soon as it exhausted its fuel. The flight was designed around the immediate removal of hardware that had finished providing thrust. As the spacecraft approached its target, navigation shifted to a selenocentric reference frame. Selenocentric refers to a coordinate system centered on the Moon rather than the Earth. To enter orbit, the surface propulsion system fired on the far side of the Moon, out of radio contact. This lunar orbit insertion placed the craft into a stable 100.9 by 122.4 kilometer orbit. At 1744 UTC, the lunar module, Eagle, physically separated from the command module, Columbia. Eagle performed a pirouette maneuver, rotating in front of Columbia so Michael Collins could verify the landing gear was intact and correctly deployed. Once undocked, Eagle was a dedicated landing craft with no heat shield and no capacity to return to Earth on its own. During the powered descent, Eagle began flying long, passing landmarks ahead of schedule. This was caused by mass cons, concentrations of high mass in the lunar crust that create gravitational anomalies and altered the descent trajectory. Exactly 6,000 feet above the surface, the computer triggered the first 1201 and 1202 program alarms. These codes appeared on the D-Sky interface, signaling that the system was being overwhelmed with data. The root cause was an electrical phasing mismatch in the rendezvous radar. This hardware mismatch sent a continuous stream of spurious, cycle-stealing data directly into the Apollo guidance computer. The computer maintained operation through an executive overflow architecture. Executive overflow is a software design that allows the system to recognize when it is overloaded and systematically drop lower priority tasks. This visualization shows the task scheduler reacting to the radar noise. To keep the core descent engine routines firing, the software dropped lower priority background tasks, prioritizing the most critical flight calculations. The landing was maintained by an asynchronous software architecture designed to prioritize survival calculations over non-essential data processing. At 300 feet, the automated landing system was targeting a boulder field near West Crater. Armstrong transitioned to semi-automatic control, pitching the craft forward to manually extend the flight path to a clear patch of ground. This schematic shows the fuel tanks during the manual maneuver. The horizontal movement caused propellant to slosh away from the sensor, triggering a premature low fuel warning in the cabin. Armstrong monitored the descent until 67-inch surface probes hanging from the footpads touched the Moon, triggering the contact light. The engine had to be shut down immediately upon contact. In the vacuum of the lunar surface, exhaust blowback from the engine could have ruptured the descent stage. Eagle landed at Tranquility Base with approximately 50 seconds of powered flight remaining. The final 100 feet required the pilot to manually override the automated landing coordinates and the false fuel sensors. This intervention allowed the craft to reach a clear landing site that the automated system had missed. To return to orbit, the astronauts used the descent stage as a launch pad, firing the ascent engine and leaving the base on the Moon. After the rendezvous and the trans-Earth injection burn, the crew discarded the ascent stage in lunar orbit. During the approach to Earth, classified military weather data indicated a severe storm front at the primary recovery zone. The winds in this area were strong enough to tear the capsule's parachutes. Mission Control adjusted the trajectory, moving the landing target 215 nautical miles to the northeast. This graph compares standard entry to the executed skip-out trajectory. By bypassing the standard P-66 reentry program and moving directly to P-67, Columbia utilized aerodynamic lift to skip along the upper atmosphere, extending its glide path safely over the storm. Columbia splashed down 24 kilometers from the recovery ship, the USS Hornet. Reaching the backup landing site required a non-standard transition between software routines to bypass the local weather hazards. A macro view of the Earth-Moon system shows the complete Figure 8 mission trajectory. This path requires shedding mass. SI-C fell in the Atlantic, SI-2 in the Pacific, SI-4D in solar orbit. The descent stage remains at Tranquility Base. The ascent stage was jettisoned. The service module burned up. Only the command module returned. This sequence of shedding mass was the exact method used to achieve the delta-V required for the mission. Delta-V is a measure of the impulse needed to perform a maneuver or change a trajectory. Throughout the flight, technical limitations were addressed through asynchronous software scheduling and direct human intervention. The technical legacy of Apollo 11 is defined by modular systems engineering, the management of vehicle mass, and adaptive software architecture to maintain critical flight functions.